Okay, so let's start with the part 3 of the chapter on graphs, and let's see what we're going to cover in here. So we are going to be covering the third part, representing graphs and graph isomorphism. So how to represent graphs in the form of matrices. So we've covered a little part of this when we did directed graphs and relations, but there are going to be a lot of similarities between what we did in relations chapter, representing relations in the form of graphs and matrices, and representing graphs here in terms of matrices. All right, and then finally the concept of graph isomorphism. We are not going to cover the topic of connectivity. All right, so the final topic in this chapter is going to be how to represent graphs in the form of matrices and the concept of graph isomorphism. All right, so what is the section summary? So the different ways in which you can represent graphs are listed right here. You can represent a graph in the form of an adjacency list or an adjacency matrix or an incidence matrix, right? So we're going to look at each of them with examples to learn how to take a graph with basically vertices and edges and represent it in the form of a matrix or a list. Now, the final topic that we're going to cover is isomorphism of graphs. So, on a high level, when two graphs are kind of similar, you say they are isomorphic in nature, right? So we are going to basically try to learn and identify how and when can we say that two graphs are identical to each other. All right, so that is what is going to be covered in isomorphism of graphs. Okay, so let's start with different various representations of graphs. So let's start with the first kind of representation, which is in the form of an adjacency list. All right, so let's look at the definition of an adjacency list. So an adjacency list is used to represent a graph without multiple edges by specifying the vertices which are connected to any given vertex in the graph. All right, so the point to be noted here is that you cannot represent a graph with multiple edges, right? So you can only represent graphs which do not have multiple edges running between two vertices using an adjacency list. Right, so here we have two examples of two example graphs, right? The first one is a simple graph, right? And the second one is basically a directed multi-graph, right? So the first one is a simple graph. There are no loops, there are no multiple edges between vertices, and the graph is undirected. Okay, the second example here basically is a multi-graph which is directed, right? That means the edges have directions. There are edges with multiple there are edges with multiple there are edges which are multiple between two vertices. However, they are in opposite direction, right? Because you cannot have multiple edges between two vertices. You cannot represent that in an adjacency list. You're considering a multi-graph which has loops. However, it does not have multiple edges between two vertices. We are only considering multiple edges which are in the opposite direction, right? So let's look at how this can be done. So the adjacency list for the first graph is given right there. Okay, so how do you list using an adjacency list? An adjacency list has two columns. Okay, so the first column is going to list all the vertices in the graph, and the second column is actually the list of vertices that this vertex is directly connected to. Okay, so let's take each vertex. Okay, so let's start with vertex A. So what are the vertices that A is connected to? A is connected to B, A is connected to C, and A is connected to E. So the adjacency list for A is going to be B, C, and E as shown in the figure. Now let's look at the vertex B. So the only other vertex that B is connected to is A. So the adjacency list of B is only going to list A. Right? Now what next? So let's look at the vertex E. E is connected to A, C, and D. So E, you can see that, is connected to A, C, and D. Let's look at D. All right, so D is connected to C and E. So that's what is given right there. And C is connected to A, E, and D. And that's what is given right there. So another important thing to remember is we are just following an alphabetical order while listing the vertices here and going from A through E, but you can list them in any order that you want. Okay, it does not matter which vertex and the adjacent vertices you list first. Okay, so now let's take the example, the second example, which is a directed multigraph, right, with loops in it. Now, so in here, let's pick a vertex, right? So you are going to list all the edges, all the vertices that are connected to A through an outgoing edge from A. Right? That is important in here. So A, there is an outgoing edge from A to B. There's an outgoing edge from A to C, from A to D, and A to E. Right? So A has an outgoing edge from A to B, C, D, and E. So all four of those are listed here. Okay, so let's take another one. So what about B now? So B has an outgoing edge to itself. There is a loop from B to B, right? So B has an outgoing edge to itself. Where else does it have an outgoing edge to? B has an outgoing edge to D. That is all. There are no other outgoing edges from B. Okay, so the adjacency list of B is going to contain the vertices that it is directly connected to, which is B and D. Okay, so let's take a look at E. E has an outgoing edge to D. E has an outgoing edge to C, and it has an outgoing edge to B as well. All right, so E is connected to B, C, and D. Now let's take a look at C. All right, so C has a loop. So C has an outgoing edge to itself. C has an outgoing edge to A and E. So it has A, C, and E in its adjacency list. Now what about D? So if you look at D, D only has incoming edges towards it. There are no outgoing edges from D. So the adjacency list for D is basically blank. It does not contain any vertices listed alongside in the adjacency list. Right, so that's the difference between how to basically list the adjacency adjacent vertices of a given vertex in case of a undirected graph as shown in example 1 and a directed graph as shown in your example 2. All right, so now moving on, let's take a look at how else you can represent a graph. So the other way of representing a graph is using an adjacency matrix. All right. So one thing you could not do with basically a graph with multiple edges between two vertices was you could not represent it using an adjacency list. However, you can definitely list multiple edges between two vertices using an adjacency matrix. Right, so let's look at a basic definition. Right, so let's first see how to represent a simple graph before going on to multiple edges and so on. So let's say you have a graph G and it's a simple graph. all right? That's what is given to you. That's what is given to you. And the number of vertices in the graph is n, all right? Then you are going to end up with an n by n matrix, right? So n rows, it's going to have n rows and n columns, right? So basically the size of the adjacency matrix depends on the number of vertices in your graph, right? So if it has n, you are going to end up with n rows and n columns. Okay, now so basically that's what it's going to look like, and you're going to fill each of the positions, right? Each of the positions in your matrix using either a 0 or a 1. So the positions, the matrix is made up of only zeros or ones, right? So let's take a look at this. So the adjacency matrix is going to contain a 1 in its ijth entry, right? When there is an edge between vi and vj, when there is a edge between the vertex vi and vertex vj. And if there is no edge between vi and vj, you put a 0 in the ijth entry. Okay, so we're going to do an example real quick, so it's going to become much more clear, right? So in other words, right, your adjacency graph is represented by a sub g, is made up of either ones or zeros. So aij here can be either a 1 or a 0, and it's going to have n rows and n columns if the number of vertices in the graph is n. All right, and how do you find out whether aij is a 1 or a 0? Aij will be a 1 if there is an edge between the vertex vi and the vertex vj. If there is no edge between those two vertices, then you're going to put a 0 in there. All right, so let's take a look at some examples to understand how to represent a given graph in the form of given simple graph in the form of an adjacency matrix. So here are two examples. So in the first example, we have a graph, and there are 4 vertices in the graph, A, B, C, and D. All right, so your number of vertices in the graph is basically 4. So your adjacency matrix is going to have 4 rows and 4 columns. So it's going to be a 4 by 4 matrix. So it has 4 rows here, and it has 4 columns as well. Okay, so now we are going to see what is represented by the rows and columns, right? So what you're going to do is write basically the vertices in a certain order next to the rows and columns. All right, so let's say this is representative of A, second is B, C, and D for the rows. The same way A, B, B, C, and D for the columns. Okay, so now we're going to see A has edges. A has edges from A to B, A to C, and A to D, and nothing from A to itself. So between A and A there is no edge, so that's going to be a 0. But there is an edge from A to B, A to C, and A to D. So A to B, that's going to be an edge. That represents a 1, and then from A to C there is an edge, so you put a 1 there. A to D there is an edge, so you put a 1 there. Now take a look at B. Okay, so take a look at B. From B you have an edge to A, you have an edge to C, but there is no edge to D. Okay, so from B to A, yes, there is an edge, so you have a 1 there, and then you have no edge from B to itself, so you put a 0 there. From B to C, yes, there is an edge, so you put a 1 there. From B to D, there is no edge, so you put a 0 there. Okay, now let's look at the next vertex, which is going to be C. So C has an edge to A and B, and there is no edge from C to D. So C to A, that represents C to A. C to B, there is an edge. And then C to itself, there is no edge, so that's a 0. C to D, there is no edge, so that's going to be a 0. Now let's look at the last vertex here, which is your D. Okay, so D just has an edge to A. D does not have an edge to itself. D does not have an edge to B or C, right? So from D to A, there is an edge. So you have a 1 representing that. And there is no edge from D to B, C, or D. So you have all zeros to represent that. Okay? So that is how you come up with the adjacency matrix for a given graph. All right, so let's take a look at the second graph here. So once again, there are 4 vertices, so it's also going to be a 4 by 4 matrix that you're going to end up with. So there are going to be 4 rows and 4 columns. Okay, and then you are going to basically fill in the positions in there with either a 0 or a 1, depending on whether there is an edge between the 2 vertices or there isn't. Okay, so I'm going to leave the second example as an exercise for you to figure out how to come up with the adjacency matrix for this. And I'm also going to give you I'm also going to post the homework today, so you can actually work on examples of how to basically draw the adjacency list or adjacency matrix and so on for a given graph, right? So you can practice some problems there. All right, so what is given in here? Right in here, what it says is that if you have a sparse graph, right, that means if you have a graph which has very few edges between the vertices, okay, then you are going to end up with more zeros in your matrix than ones. Okay, so then what you end up with is a sparse matrix. So if you consider ones as information and if you consider zeros as a lack of information, then you have very little information that you're getting from an adjacency matrix. Right, so that is a case where probably you're better off using an adjacency list to represent a graph rather than use an adjacency matrix. Okay, so when you have a graph which is dense, that means there are too many edges between the vertices, more like a completely connected graph, then you're better off using an adjacency matrix. But if you have a sparse graph, okay, that means there are very few edges connecting the vertices, then you're better off using an adjacency list. All right, now another important thing to remember is that your adjacency matrix of a simple graph, this is not true for any graph, for a simple graph is going to be symmetric. All right, that means the Aij and Abi positions are going to be the same. All right, that makes sense, right? If there is an edge between A to B, then there is also an edge from B to A, right? So the number that is depicting edge AB and the number which is depicting edge BA is going to hold the same value, right? And that's going to be the same for every position, right? So what this says is you're going to end up with a matrix where your lower triangular matrix, which is that part, is going to be similar to your upper or it's a mirror image of your upper triangular matrix. All right, and another thing is that your diagonal elements are all going to be 0 because there are no loops in a simple graph. Alright, so as I mentioned before, you can use an adjacency matrix to not only represent a simple graph, but also graphs with loops and edges, multiple, basically multi-graphs as well, right? So how do you represent a loop? A loop is basically represented by a 1 at the diagonal position, all right? It's going to be a diagonal position for that given vertex, okay, at the ijth position of the vertex, right, for the vertex. So in the matrix, one of the diagonal values is going to be a 1 if there is a loop in your graph. So how do you represent multiple edges? Right? So if there are multiple edges which are connecting two vertices, then right now you're not going to just say either a 0 or a 1. Okay, if there are multiple edges between two vertices, you're going to count how many edges are there between the two vertices, and you're going to write that number instead of just a 1. Okay, so that is the main difference about how you go about basically representing an adjacency matrix for a graph which has loops and multiple edges. So here we have an example, right? So here we have an example right here, which is representing a multi-graph. As you can see, there are multiple edges between vertices, and there are also loops in the graph. So once again, there are 4 vertices, right? So you're going to end up with a 4 by 4 matrix. So let's write down the vertex it's representing, the row and the column, okay, next to it. So B, C, and a D, and then here you have A, B, C, and a D. Okay, so let's take a look at how to represent for A. Okay, so A has three edges connected to B. So A has no loops, first thing, so that's going to be a 0. Okay, from A to A there is no loop. From A to B there are 3 edges, so instead of a 1 you're going to have a 3 right there. Okay, now from A to C there is no edge, so that's a 0. From A to D there are 2 edges, so that's going to be a 2 instead of a 1. Okay, now let's look from B to A. So B to A, once again you have three edges, so that's going to be represented using the number 3. Then we have no loop at B, so that's going to be B to B, that's a 0. And then you have from B to C there is a single edge, so that's going to be represented with a 1. From B to D there is a single edge, that's going to be represented using a 1. Right? Now from C to A there is no edge, so that's going to be represented using a 0. All right? From C to B there is a single edge, so you have a 1 there. C to itself, C to C. So now if you consider C, there is a loop, right? So you have a 1 in the diagonal position, right, for C comma C. All right, next is from C to D, there are 2 edges. So you're going to have a 2 to represent that. Now let's take a look at D, right? So D has 2 edges to A, so that's going to be a 2 there. D has a single edge to B, so you have a 1. D has 2 edges to C, that's going to be a 2. D does not have any loops to itself, so that's going to be a 0. Right? So now this is how you represent a multi-graph with loops and multiple edges using an adjacency matrix. All right, so now let's take, so far we have been looking at adjacency matrix and how you can represent a simple graph or a multi-graph using an adjacency matrix, but for an undirected graph, right? So adjacency matrices can also be used to represent a directed graph. All right, so once again, just like we did an adjacency list, right? So we are going to see if there is an edge from Vi to Vj, all right? And then Aij element is going to be a 1. That means a row I column j will be a 1 to represent an edge from Vi to Vj. Right? However, it's not going to be symmetric in nature. All right, the directed graph is not going to be symmetric in nature. So just because Aij is, let's say, 1 or a 0 does not mean Aji will be the same as Aij. Okay, because Aij represents an edge that is going from Vi to Vj. All right. If you want to represent an edge going from Vj to Vi, that is represented by Aj. Okay, and that can be different from Aij. All right, and that is the reason why in a directed graph, you are not going to have symmetry. All right, your upper triangular matrix and the lower triangular matrix that I pointed out a couple of slides back are not going to be the same in a directed graph. All right, so once again, you can also represent a directed multigraph using the number, by counting the number of edges that are going in the same direction between two vertices and writing that number down instead of just a 1. A 1 to point there is an edge between the two vertices. So we are going to do a couple of examples of these in order to understand them, and once again there are going to be problems in your homework that I'm going to post today. That you can work on, and you can come back to me if you have questions there. Okay, so let's take the same example graph that we used for the adjacency list and try to draw an adjacency matrix for this directed multigraph. All right, so how many vertices are there in here? There are 5 vertices, so you're going to have a 5 by 5 matrix. All right, so so let's see. You have A, B, C, D, and E, 5 rows. Then you have A, B, C, D, and E, 5 columns. Okay, so now let's take a look at each of the vertices. So let's start with A. Okay, so A has, from A to A, there is no loop, so that's going to be a 0. From A to B, there is a single edge going out of A to B, so that's going to represent, that's going to be represented with a 1. A to C, yes, there is an edge. A to D, yes, there is an edge. And A to E, there is no edge. All right. So, yeah, I'm sorry, A to E there is an edge, so that's going to be represented with a 1. All right, so now let's look at the next one, which is B. Okay, so from B, B to A, there is no edge, so that's going to be a 0. B to B, B to itself, there is a loop, so that's going to be a 1, right? B to C, no edge. B to D, yes, there is an edge. And B to E, there is no edge. Okay, now let's take a look at the next one, which is C. So C to A, yes, there is an edge. C to B, there is no edge. C to itself, yes, there is a loop. C to D, no. And C to E, yes. All right, now from D, let's take a look at D now. So D does not have any outgoing edges, right? So D to A, there is no edge. D to B, there is no edge. D to C, there is no edge. D to D, there is no loop. D to E, there is no edge. Now let's take a look at E next. From E to A, there is no edge. From E to B, yes, there is an edge. E to C, yes, there is an edge. E to D, yes, there is an edge. E to itself, there is no loop, so that's going to be a 0. All right. So if you notice here, your upper triangular and the lower triangular matrix are not the same. That's your upper triangular, and then that is going to be your that's your upper triangle, and this is your lower triangle, and they are not mirror images of one another. Okay. So this is the adjacency matrix for a directed multigraph which has loops. It does not have multiple edges. The example that I took does not have multiple edges, but if you had multiple edges going in the same direction between two vertices, instead of a 1, you would actually count the number of edges that are going between the two vertices, and you'll write down the number instead of writing the number 1 there. Alright, so we looked at two ways of representing graphs. The first one was using an adjacency list, and the second one was using an adjacency matrix. Alright, now the third way of representing a graph is using an incidence matrix. Right, so in here you come up with a matrix, right? But in here, the matrix is built between the vertices and the edges. All right, so let's say you have a given graph G with a set of vertices and a set of edges. Right, you're actually going to name the vertices, right, in the given graph before you get started with drawing incidence matrix. Right, so let's say you're going to name the edges E1 through EM. Right, and then your incidence matrix is basically an n by m matrix. So if there are n vertices and m edges, then you're going to have an n by m matrix. So it's not going to be a perfect square matrix. So there are going to be fewer rows than columns sometimes, or there can be more rows than there are columns, or it is also possible to have the same number of rows or columns, but there is no saying that it's going to be a square matrix here. Okay, so now let's look at how do you come up with the matrix. So once again, the matrix is going to be made up of Mij, which can either take the value of 1 or 0. Okay, so how do you tell whether your Mij value for that position is going to be a 1 or a 0, right? So your Mij is going to be 1 if the edge Ej is basically incident upon or incident from the given vertex Vi. So if the edge is connected to Vi, if the given edge Ej is connected to Vi, then your Mij position is going to be a 1. If that given edge does not connect to the given vertex, then it is going to be a 0. Right? So we're going to look at an example of this real quick, so you are going to understand this much better. All right, so let's take two examples to understand how to come up with incidence matrices for a given graph. The first example is that of a simple graph, right? And the second example is that for a pseudograph, which contains loops and multiple edges between vertices. Okay, so in an incidence matrix, the rows are represented by your vertices and your edges are represented by your columns. Okay, so let's basically write the edges, the corresponding edges and vertices next to each row and column. Okay, so let's start with V1, then we have V2, then we have V3, and then we have V4, and then we have V5. Okay, I apologize, it's a small space I'm trying to write in, so it's not coming out very well. All right, and then along the columns you're going to write each of the edge names, right? So before you start this, you'll have to give names to your edges. It does not matter the order in which you're going to name the edges. You can follow any which order, but basically give a name from E1, E2, so on until you have covered all edges. Okay, so let's start with this. You have E1, E2, then you have E3, E4, and E5. Okay, along the columns. All right, so now let's take a look at V1. V1 is connected to E1 and it's connected to E2. So V1 and E1 shows a 1 there. V1 and E2 shows a 1 underneath, right? It's not connected to any of the other edges, so all the other edges basically have a 0 right there. Okay, let's take a look at V2. V2 is connected to E3, E4, and E6. Okay, so that is your E3 here, E4 right there, and then your E6, right? All the other edges are going to be showing zeros. Now what about your V3? V3 is connected to E5 and E6. So what do you have here? V5 and E5 and E6 show a 1. All other edges are showing a 0 right there. Okay, and that's how you continue with the rest of the vertices and edges, right, until you fill up the rest of the matrix. Okay, so now how do you represent a pseudograph? Right, so if there are multiple edges between two vertices, you're going to give each edge a new name. So if you look here, you have two edges between V1 and V2. One of them is E2, the other one is E3. So you've named them separately, and basically you are going to come up with the incidence matrix very similar to the previous example. So you're going to list your vertices here. Your edges are going to be along your columns, and if the edge is joining that vertex, there's going to be a 1 in the ijth position. Vi and ej are connected, then ijth position will be a 1. If vi is not connected to the edge ej, then ijth position is going to be a 0. So now we're done with representing the graphs using 3 different forms: adjacency list, adjacency matrix, and incidence matrix. Right? So now we're going to move on to the next concept at hand, which is isomorphism of graphs. Right? So isomorphism means when how can you say two graphs are identical or two graphs are similar? All right, so let's look at the definition that's given here. All right, two simple graphs, right? Let's say G1, which contains a set of vertices V1 and a set of edges E1, and another graph G2, which contains a set of vertices V2 and another set of edges E2, are said to be isomorphic. When do you say they're isomorphic? When there is a one-to-one correspondence and an onto correspondence from the set of vertices in the first graph to the set of vertices in the second graph, All right, and such that if two vertices A and B are adjacent to each other in the graph G1, then they're also going to be adjacent in your graph G2. All right, or the corresponding vertices in your graph G2 are also going to be adjacent. All right, so such a function, if you can come up with such a function that can map the vertices in your graph G1 to the vertices in your graph G2, then you can say that the two graphs G1 and G2 are isomorphic. If you cannot come up with such a correspondence between the two graphs, then you say that the two graphs are basically non-isomorphic. Right? If you can come up with such a correspondence or such a function, it's called, the graphs are going to be called isomorphic. And if you cannot do so, the two graphs are going to be called non-isomorphic. All right, so let's take a simple example here. So we have two graphs, all right, given right here, the graph G and the graph H, all right, and show that they are both isomorphic. So how do you show that both of them are isomorphic? Right, so we are going to find similar vertices, all right, which are basically have a correspondence, all right, or a one-to-one mapping with respect to the edges they are connected to in both the graphs. Right, so let's say you find a mapping from U1 to vertex V1, right, in graph G to graph H. U2 has a correspondence to V4, right? U3 has a correspondence to V3, and U4 has a correspondence to V2, right? Now, not only will there be a correspondence between the vertices, but they have to have a map with also with respect to the edges. All right, that means the pair of vertices, let's say V1 and V4 has an edge. Okay, so you have V1 and V4 has an edge, and what is the corresponding vertex in the other graph? U1 and U2 also has an edge in graph G, right? V1 and V4 has a edge in your graph H, and U1 and U2 has an edge in your graph G. Okay, very similarly, if you look at the other edges as well, V1 and V3 has an edge in your graph H. Okay, and what is the corresponding vertex for V1? It's U1. And what is the corresponding vertex for V3? It is U3. So U1 and U3 also has an edge between the two. So if you pick any pair of vertices, right, in graph G, and the same corresponding pair of vertices according to the function that has been given here, right, there will be an edge between both pairs of vertices in both the graphs, or there will not be an edge between both pairs of vertices from both the graphs. Right, so since we are able to find such a correspondence with respect to vertices and also with respect to edges, you say that the graph G and H in this example are isomorphic in nature. All right, so now let's take another example. All right, so we are given two graphs again here, graph G and graph H. Can you tell if these two graphs are isomorphic, right? But the answer here is that the graph G and H are not isomorphic, because you cannot come up with a direct correspondence between the vertices in graph G to vertices in graph H. Very simply put, right? So let's look at graph G. So there are two vertices which have, let's say, degree 2, and two vertices which have degree 3. Okay, so the vertex that has a degree 2 is connected to two vertices which has degree 3, and the vertex which has degree 3 is connected to two vertices which have a degree 2. Right, that is what is happening in your graph G. However, in your graph H, right, the two once again there are two vertices with degree 3, and then there are two vertices with degree 2. However, the two vertices with degree 2 are connected together, and the two vertices with degree 3 are also connected together. Okay, so you can easily tell that you cannot find a correspondence of vertices between the two graphs G and H. All right, and so therefore they are not isomorphic to one another. All right, so let's take another example here to tell if the two given graphs are isomorphic or not. All right, so we have learned a couple of tricks from the previous slide. Okay, the previous slide told us that you can count the number of edges and the number of vertices and see if they're equal in both the graphs first before going on to find a one-to-one correspondence. All right, so what do we notice here? Both graph G and H has 6 vertices. Both graph G and H have 7 edges. So that is the first thing that you need to check when you want to find a isomorphism between two graphs, right? So which checks out in this case, right? The next thing is you want to find the degree of each vertex in G, list it, define the degree of each vertex in H and list it, and then try to find a one-to-one correspondence. So here what do you have? U1 has a degree equal to 2. U3 also has a degree equal to, 2. U4 has a degree 3. U2 has a degree 3. And then U4 and U6 both have a degree 2. Okay, so now the same way list the degrees for each of the vertices in your graph H. Right, and then try to find the correspondence between the vertices which have the same degree. All right, and then after a couple of trials you will be able to find the function that will give you the correspondence between the vertices in graph G and graph H. So the function that determines the correspondence between the vertices in graph G and H is given right there. Right, so as an exercise I want you to sit down and see if the vertices correspond to one another, and also the edges connected to those vertices and the degrees of those vertices correspond to one another. All right, so let's go back one more time. So in order to tell if two graphs are isomorphic, first thing you want to start with is counting the number of vertices in both the graphs. If they're equal, then go to step 2, which is count the number of edges in both the graphs. If both of that is equal, then list the degrees of each of the vertices in both the graphs. Right? Then if the degree list is the same, right? If the degree list is kind of same, that means if you have two vertices with degree 2, 2 with degree 3, and 2 with degree 4 in both the graphs, that means it is possible to find it is definitely possible to find an isomorphism here. Then try to find a function, right, with vertices from one graph with vertices with other graph which have the same degree. All right, so these are the steps that you would want to follow in order to determine if the two given graphs are isomorphic. All right, so I'm going to give you several examples in your homework that I want you to work on and basically determine if two graphs are isomorphic or not. So with this, we are at the end of a chapter on graphs, right? And I'm going to post this as well today, and also the homework is going to be up, which is going to be on all the topics that we have covered since our second midterm, right? The homework is not going to be due, right? It's not going to be due for you to turn it in, right? It's not going to be graded either. You will have from now till the end of the semester, and it's going to be more like a practice homework, right? You do not have to turn it in for a grade. Okay, so you have all the time to work on those problems, and you can come back to me either in the class or during office hours if you have questions with the homework. All right. Okay.